Now let's talk about the virtual memory. Till now I have been talking about virtual memory, but not in a, I didn't show you any practicality about this. But let's now talk about the virtual memory in complete. So the main advantage of virtual memory is whenever the process size is very much big than main memory, it will let the operating system help us in running such a process. So what is the advantage? A user will get the illusion that it is just an illusion. A user will get the illusion that, oh, the main memory is available to load his complete memory, or when the user is writing the program, he will never think about what will be the size of the main memory on which this particular program will be executing. He will write the process in such a way, that program in such a way that it will fit in the secondary memory. So if the hard disk is, let us say, 1 terabyte, he can go up to 1 terabyte of program. That is not actually possible. I mean, these big programs are not actually possible, but still a user can think that there is lot of memory at his disposal, and the memory, that main memory, is equal to the secondary memory. That is the illusion operating system will create. So how does it exactly work? This way, watch it. So generally, whenever you create a process, let's say the process is initially residing in the secondary memory, right? Therefore, your virtual address space is limited by the secondary memory space, and secondary memory is generally cheaper. The hard disk is cheap, right? Terabytes of hard disk is quite common these days. Therefore, your process can be very big, and they can reside in the gigabytes or anything. They can reside in the secondary memory. Let us assume that there are two processes, P1 and P2. Now, without the concept of virtual memory, what people used to do is they used to completely load a process in the main memory and then they used to run it. But now, with the introduction of virtual memory, you need not completely load the process in the main memory. You can load only a part of the process in the main memory and you can run it. What is the advantage? One thing is the size of the process itself is greater than the size of the main memory. Second thing is I am actually conserving the main memory, which means by not filling up the main memory with one process, I am just letting the space be there so that I can put many processes. Using this, the degree of multi-programming can be increased. What is degree of multi-programming? At any time, the number of processes which will be residing in the main memory and that will be available for running is degree of multi-programming. Now, when I put only a part of the process, I can put many processes in the main memory. That is how the degree of multi-programming can be increased. And I already told you that with the degree of multi-programming increased, CPU utilization will increase. Therefore, virtual memory not only helps us in running the bigger programs. That is the initial advantage number one, or the main purpose of the virtual memory is to run program which is bigger than main memory. But then later it got converted in such a way that using the virtual memory, we are able to increase the degree of multi-programming, and so the CPU utilization is also going to be increased, right? So now virtual memory has these many advantages. So almost every operating system these days is using virtual memory only. Even every device is using virtual memory, which means no one is actually loading everything onto the main memory, and no one is going to put a lot of burden on the main memory. They are going to load a part of the process which is required into the main memory and run it, and then replace it with the other pages as required. Got it? So let's see this example. There are two processes, P1 and P2, and we are not going to load the entire part into the main memory because main memory will not be sufficient for that. And this is the main memory. Process are divided into pages. Here it has 8 pages, process P1, and process P2 has 8 pages. And now the main memory has frames, and 16 frames are there, in such a way that page size is equal to frame size. And in the main memory, the top 3 frames are given away for the operating system. So operating system is always going to be resident in the main memory. Therefore, we have to dedicate it some space, and in the remaining space, and remember this, loader should always be there in the operating system. I mean, should always be there in the main memory, because loader is used to load many other things, right? Therefore, loader is always supposed to be there. Okay, if loader is not there, we cannot load any other things. Okay, and now once the operating system has decided about the boundary, that this is the system space and this is user space, in the user area the processes are going to be loaded. Now watch it. Now frame number 3 is loaded with page number 1 of process 1. P1 means, capital P means the process, small p means the page. Therefore frame number 3 is loaded with page number 1 of process 1, and frame number 4 is loaded with page number 2 of process 1, and frame number 5 is loaded with page number 3 of process 2, right? So if you observe it, it is not only that only a part of the process is present in the main memory, even these parts are present non-contiguously, which means there is no contiguity in the in the process arrangement. So that is one more advantage. What is the main advantage of letting a process be at any place? External fragmentation will be 0, right? But still internal fragmentation is there. I told you in the previous question, right? Internal fragmentation is there, and that will be roughly equal to half of the page size, right? Okay, now watch it. Now if you watch it, process P1 is present at 4 places: process P1, process P1, process P1 and process P1. And if you watch it, page number 1, page number 2, page number 3, oh, this is process P2, page number 3 and page number 4. Page number 1, 2, 3, 4 of process 1 are present in the main memory, and the other pages of process 1 are not present. And if you watch the process 2, page number 1, page number 3 and page number 7 and page number 6, which means 1, 3, 6, 7 are present in the main memory and others are not present, right? So accordingly, your page table, and every process will have a page table. Since there are two processes, there will be two page tables, and page table 1 represents what are the pages of process 1 which are present in the memory, and what are the pages of process 1 which are not present in the memory. Now if you watch it, this is the page table of the process 1. This entire thing is the page table of the process 1. How many pages are present in the process 1? 8 pages are present. Therefore page table will contain 8 entries representing each page. Now if you see this, if you look at this process 1, one more thing, whatever I am showing you here is a snapshot, which means the system is running these processes, and at some point of time this is what has happened. It doesn't mean that the process started out with this or the system started out with this. Initially there are various cases. There is no need or there is no necessity that there has to be at least few pages of a process present in the main memory to start it, right? No need. And whatever I am showing you here is a snapshot of the system at some point of time, right? Okay, now if you watch it, this page table 1 of process will say which pages are present in which frames. Now it is saying that page number 1 is present in frame number 3 of process 1. Page number 1 is present in frame number 3, isn't it? Frame number 3 contains page number 1, and similarly it is saying that page number 2 is present in frame number 4. So go to frame number 4, page number 2 is present. Similarly, page number 3 is present in frame number 8. Page number 3 is present in frame number 8. Page number 4 is present in frame number 10, right? Now, whenever you are searching for a page, first thing is in virtual memory, you should be you should first think about whether the whatever page you are looking for is present in the main memory or not, because the chances are that it might not be present. So in order to differentiate whether a page is present in the main memory or not, we are going to use one bit to differentiate it, and that bit is valid invalid bit. So valid invalid bit is going to say whether the page that you are looking for is present in the main memory or not. Now if you watch it, page number 1, 2, 3, 4 valid bits are 1, which means these pages are present in the main memory, and for all the other one, valid bit is 0, which means these pages are not present in the memory. So whenever you try to refer to a page, if it is already present in the main memory, you will go to the main memory and do it, take it. If it is not present in the memory, that is called as page fault. Page fault is whenever the page you are looking for is not present in the main memory, then you are supposed to get it from the secondary memory, right? How can you get it from the secondary memory? We go for a page fault. So whenever we declare a page fault, then the operating system is going to get that page and load it in the memory and again restart the process. Got it? So valid invalid bits are used for knowing whether it is page is present or not. And next one is dirty, this D bit. So there are various entries which are present in the page table other than this frame number, and the next important thing is D bit. D means dirty bit. So dirty bit, or it is also sometimes called as modified bit. this d bit says, or this d bit will say whether the page after getting loaded into the main memory has been modified or not. Why should we know it? In case, let us say d bit of this one is 1 and 0 0 1 0 0 0 0. If this is the scenario, then it means that the page number 1, which is present in frame number 3, has been modified at some point of time. Therefore, now since it has been modified, it has to get reflected in the secondary memory as well. So whenever we try to replace the page number 1 of process process P1, we are not just supposed to overwrite on that, we have to write it back, right? That is called as write back. Write back means when we have various levels of memory, and whenever anything gets modified in the higher level, which means in this case main memory, it has to get reflected in the lower level, which means the secondary memory. That is called as write back. And when do we do write back? The best time is not always, right? Whenever we try to replace it, whenever we try to write something over it, whenever we try to overwrite something on that frame, it is better you write it back and then get the new page. So in case if this page 1 of this process is going to be has to be replaced, then we are going to write it back first and then load the new one. That is why dirty bit is going to be used. And next one is referenced. So reference will this is called reference bit. Reference bit will just say in the last clock cycle what are the pages that are referred, right? Which means this bit will keep on changing. In the last clock cycle, if some bit has been referred, it will be marked as 1. If it has not been referred, it will be marked as 0, right? So every clock cycle, reference bits are going to change depending on what are the pages that have been referred in the last. Why is this important is, once we know what are the pages which have been referred, then it is very easy to replace them. So generally most of the algorithms will say that if a page has not been referred in the last clock cycle, or it has been not referred for a long time, the chances are that it might not be referred in the future, right? I mean, that is the assumption. So many of the algorithms will do page replacement. What is page replacement? If I have only few number of frames to run my process, and if I already loaded with all the pages, and if I need a new page, then one of the existing pages have to be replaced, which means in this case, the total number of frames that are given to this process P1 is 3, 4, 8, 10. These frames are dedicated to process P1 as of now, right? Then most of the algorithms, they'll try to use these dedicated frames in order to run the process. Then what happens is, when we have 3 frames, 3, 4, 8, 10, and right now they are holding the process pages, page 1, page 2, and page 3 and page 4. And if I need a new page number 5, then one of these pages have to be replaced, right? Then which one is more suitable? There are various versions and various arguments about it, and one particular argument is pull out the page which has not been referred in the last clock cycle. So just to differentiate whether a page has been referred in the last clock cycle or not, we are going to use this OR bit. So OR bit is going to say which process are referred, which means let us say this is 1 1 0 0, and all the others anyway are going to be 0. They are not present in the page table, I mean in the main memory. How will they be referred? So it means that in the last clock cycle 3 and 4 are referred and 8 and 10 are not referred. Therefore if you try to replace any of the pages, then the better options will be page number 3 and 4 because they are not referred, right? And the last one is protection bit. P bit means protection bit. What does protection bit indicate? Whether you have rights to do some kind of access. Sometimes what happens is, I told you there are 3 kinds of sections. One is data section, and other is code section, and other is stack section. And if you are in the code section, you are not supposed to modify the code, right? So whenever you are trying to access the main memory, and when you are trying to write something on the code, then this protection will catch you. Which means if the CPU has got an instruction to modify a page which is actually a code, right, then the protection section will catch you. So this protection will contain various bits like read, write, execute, right? Generally Code section will be read and execute permissions. Data section will be read and write. Stack will be read and write, right? So if you try to access these sections using any other type of access, then your there will be a page, there will be a trap means you are not supposed to do any other kind of actions other than which are permitted on that page. So generally a page will have some permissions. If it is a code page, you have to only read and execute. If it is a data page, read and write. Stack, read and write. So that is how various other informations are going to be useful. And one interesting thing is, even this page table whatever I have shown you, see, the process is present in secondary memory, fine, and now a part of process is present in main memory, fine, and the information about which part is present in main memory is present in the page table, and now even this page table has to be in the main memory, which means even this entire page table is again going to be present in the main memory, right? So I'm assuming that in this case we are lucky that the page table is fitting in one frame. In that case, I need only one level of paging. So in this one level of paging, this page table is present in the frame number 11. So process has to be present in the main memory. Along with that, its page table also has to be present in the main memory. Yes, it is present in the main memory. And now, where is the page table? That CPU should know it. So even though CPU does not know anything about where the process is present, it is fine, but at least CPU should know where the page table of the process is, so that it will start searching for page table first, and then it will start searching for the page first, page number, and then the frame, right? So now, since this is present in frame number 11, in case if process P1 is executing in CPU, watch it, CPU is going to have like this. CPU is going to have a register which is going to say what is the page table base address. Page table base address means where is this page table loaded. So it is containing frame number 11, which means CPU now knows that page table is present in frame number 11. So inside this frame number 11, this entire page table is present. Now what is the advantage of this? Now whenever any CPU generates logical address, I told you logical address is of two parts. One is page number and other is page offset, right? Now we take the base of the page table. This will tell us where the page table is loaded, and then we take the page number and then we add it. Then we can exactly go into that particular page number of the page table. So using these two, I can get into the page table of the required page. Let us say the page number required is 3, right, and the offset required is some x. Okay, now I went into this page number 3 entry of the page table. Now it is saying that valid bit is 1. Valid bit is 1 means yes, it is present in the main memory, and if the valid bit is 1, then only I am going to look at the frame. Along with that, I am going to even see the permission. Let us say I want to read the memory, and now I'll check whether I have reading permissions or not. Generally reading permissions will be enabled for all the pages, right? Therefore now I'll observe that, oh, page number 3 is present in frame number 8. So I'll take this frame number, right? I'll take this frame number 8, and then I'll do this page offset as it is, and it is called as physical address. Using this physical address, now I can access the main memory. In the main memory, I'll go into the frame number 8 and I'll get the corresponding word. Understood this? So one thing you should notice, even the process is present in the main memory, as well as page table also has to be present in main memory. In case if page table is too big that it cannot fit in one page, we have already seen it, that is called as multi-paging. In multi-paging, we are going to go till the level so that the last level will contain a page table which can fit in one page, right? Okay. Similarly, the same thing is true with the page, process 2 also. Process 2 is loaded in frame number 3, the page table of process 2, and I didn't show you all the bits. You can fill them up, right? What are the main entries are? Watch it. Process 2 page number 3 is present in frame number 5, which means page number 3 of process 2 is present in frame number 5, and again process 2 page number 1 is present in frame number 6, right? And again process 2 page number 6 is present in frame number 7, and process 2 page number 7 is present in frame number 9. Got it? So this is how the page table will be filled up, and you will have valid bits as 1 1 1 1 and then 0 0 0 0. So whenever we switch the context from P1 to P2, which means we stop running P1 and we have to start running P2, then this page table base will now be loaded with the base address of this page number 2, which means it will now get loaded with 13, and all the other registers will also be changed appropriately. Got it? So this is what happens in the virtual memory. In virtual memory, we are not going to have entire process in the main memory. We are going to have only a part of it. And how can we keep track of which part is present? Using the page table, using the valid bits. Along with this, there are various bits, right? Whenever valid bit is 1, it means the page is present. If the valid bit is 0, it means the page is not present, and that will lead to page fault. What is page fault? If the page is not present, then we are going to block the process and put it in the block state, and we ask the main memory, the secondary memory, to load that particular page into the main memory, and then we start running it. Therefore, whenever there is a page fault, the time taken is going to be very high. So let's talk about page faults also. Okay.